Right. Hopefully everyone can hear me online. Yeah, we're just gonna get started because we've got yet again a lot to get through this lesson as well. So pretty much today we've moved on to rigid bodies, rigid body dynamics, and yeah, as you can see in my lesson plan, it's quite packed. But that's mostly just because I want to jump back and forth between a bunch of small concepts before I move on to like the next questions. There is a question 4 on Moodle in the workshop problems, but I won't have time to run through that in my lesson plan because yeah, we'll probably have quite a packed lesson. But the solutions for those workshop problems will be released online, usually after the tute. Yeah. And so, yeah, basically a little forewarning. Pretty much today's lesson is probably the hardest topic in the course. Like rigid bodies in general is quite difficult. But I think in particular, the kinematics part, you use a lot of different like techniques that you've been using throughout the course, like the velocity diagrams, unit vectors. I've alluded to a few of these things early in the course, but it's like cranked up to 11 in this workshop. But surprisingly, next workshop, which by the way is on Friday, I've confirmed, not Thursday, so it's on the public holiday. Yeah, I understand that's like inconvenient for a lot of people, particularly like if you're taking public transport or whatever, the buses might not run as often. But yeah, it's going to be hybrid like normal, so you can tune in online or whatever if that suits you better. But yeah, anyway, so surprisingly, that lesson on Friday won't be as hard. That one will be on kinetics, and yeah, if you have practiced your work energy methods and your impulse momentum methods, that's 2/3 of the tute already, pretty much. It's very similar to what you've learned for particles. Yeah. Anyway, so without further ado, Oh, actually, one more thing. Yeah, I'll just remind everyone again that my experience is out. I'm not sure when it closes. I assume it closes either on the weekend or early next week. But yeah, if you enjoyed this course, or if you didn't, whatever, just please make sure to leave a review so we can improve the course for future years. And yeah, and then it can give us feedback, or like let me know if I'm doing well or whatever as well. So yeah, it's all anonymous as well for those my experience surveys. Okay, so as usual, I'm going to start quite broad with like the general concepts, and then move on to more specific formulas, and then worked examples, right? So firstly, I've mentioned the word rigid body a few times already throughout the course, so I just wanted to differentiate it from particles, right? Because particle, for example, might be something like a ball. I mean, this was in the case of projectile motion, right? So we're looking at this from elevation view. But if we were talking about, our billiard ball collisions that we were talking about last lesson as well, this is from plan view, so top down. These are also, actually, it's a bad example. Say the head-on collisions. These are more or less treated like particles, and the math still works out, right? And yeah, and for rigid bodies, we've talked about beams in the first half of the course as a 1D rigid body, but in the context of today's lesson, we'll be talking a lot about rods. Which are effectively like moving beams. The only difference is that, and you'll see at the very end of this sheet, will make a difference is it's pretty much a cylinder, right? So the shape will matter in the very last part of the tute when we start talking about what's the word for it? Mass moment of inertia. Okay. Yeah. So you'll see rods pop up. So an example of a 2D rigid body might be a rock, for example, where G denotes the center of gravity, right? And yeah, if we have our pin's reaction and it rotates like this, about this point, right? So that's your curvilinear path, which the center of gravity will follow, right? So that's an example of a 2D rigid body. By the way, in real life, this pin support might actually just be like the edge of a cliff or something like that, right? That would stop the that would stop the X and Y components for your reactions, right? But it wouldn't stop the rotation. So that's an example of what that might be for the mining engineers out there. Yeah. The other thing to talk about quickly is plane motion. So this is kind of completely new, pretty much. I haven't talked about this earlier. Well, it's been mentioned in the lectures, of course, today. But translation, right? Translation is like, for example, a car moving, it's rectilinear motion. And you might remember when we're talking about particles, we could treat the car like a particle, right? Just treat it like its center of gravity and analyze, I guess, the motion undergoing that, happening in that rectilinear path, right? But where it gets interesting is when you introduce rotation, in which, so when you introduce rotation, then rigid bodies start not behaving like particles, pretty much, right? So I'll give you an example. It's my best drawing of a windmill. Right? Where you have this fixed axis here, which is kind of where these fan blades are spinning around about the ends, right? And so that's what you would consider rotation about a fixed axis. The drawing I drew earlier of this rock is another example of rotation about a fixed axis, right? It's about this cliff edge, right? And with rigid bodies, you can also encounter general plane motion. So we can draw this well. There you go. It's like Walt Disney. So human walking or some sort of complex motion or whatever, that would be considered general plane motion, because general plane motion is pretty much anything which doesn't fall under the first two categories, which is exclusively translation and exclusively rotation, right? So this is a combination of rotation and translation, right? And so in terms of what I was talking about earlier with particles and rigid bodies, particles can undergo translation. So think of a billiard ball, but you have to start considering them as rigid bodies once you introduce rotation, pretty much, right? So imagine like a pool ball and this elevation view. You like hit it off its center, pretty much, and then it introduces a spin, and then you have to start thinking of that billiard ball as a rigid body, right? Whether in 2D or 3D, whatever. Yeah, anyway. So that's kind of how it works. Yeah. before I move on, I just want to check if anyone has any questions. Check online as well. Seems like we're good. Okay. So with velocity dynamics, here's how it generally goes. Pretty much we usually work with 1D rigid bodies. And here's the first case which I've drawn out, which is this rotation about a fixed axis. So in the context, sorry, I'm going to scroll up. In the context of what I was talking about earlier, this would be the second case, right? When you have this like pinned support, we're not talking about general plane motion. We're just talking about it being fixed here and then rotating. So this one doesn't move, right? And that's going to be pretty important for us having additional information to solve questions. Okay. So what I want to talk about is angular velocity, pretty much, right? Because the only time we've seen this in the course so far is with particles undergoing like a curvilinear path or something like that, right? But we're going to talk about it extensively this shoot because, okay, so say you have a counterclockwise spin happening here. This is pretty much the 2D representation. I don't know if that's the official term that they would be using, but that's what I call it, right? When we draw this on a page, it kind of looks like how we've been drawing our moments as well in the statics portion. But yeah, when we have this counterclockwise spin, it's because we're trying to represent this vector in 2D. Okay. Okay, I might draw what I mean by that, like here. So this is called the right-hand rule. You might remember this applying for things like something to do with electricity, I don't know, electric fields or something in physics. But it also applies here pretty much, right? Because here, this is the scalar representation of our angular velocity, and that translates to our vector representation, right, of angular velocity. So to be a bit more clear, if that's our xy plane, right, that would be our z-axis. So it's if it's a counterclockwise spin, it's pointing at the viewer, right? And yeah, anyway. So let's talk about our setup here. So R represents the distance, you know, of OA or whatever, right? Sometimes I call this using that kind of notation, right? It's just a vector notation for our radius or our distance or whatever. And basically, it's always perpendicular. Our velocity is always perpendicular to this radius, right? But just have a think about how I've drawn this counterclockwise spin about O. Is our vector going to be this one or this one? So pointing up and left or down and right? It's going to be this one, right? Let's call it V for now. So it's going to be this because this causes it to go that way, right? So it's going to move up and left, right? So very similarly to when we started solving beams back in the first and second week, you're just going to have to develop a kind of intuition of how this moves, right? And how the spin works, right? Let's write this. Okay. So one more thing to note is V. So V is going to be, it's going to be the velocity of A relative to O. Okay, so here's how you think about it. If I'm looking from O, right, that's the velocity of A, right? So therefore, with our notation, it's velocity of A relative to O, yeah? You might notice that here and here, I've called this for angular velocity omega OA, and that's just like my preferred notation, but it's because, I don't know, it just makes more sense in my head, like going from point O to A, and then that's the spin being caused there. And same with ROA, it's a vector, there. But yeah, this one, the order's switched around pretty much, right? So the velocity of A relative to O, right? So that's reflected in our formula. You might see that it's OA, but this one's A/O. So the velocity of A relative to O, right? One more thing to note is that when we have one end as a fixed end, right? Okay, let's just quickly do this. Do you remember our relative velocity equation? This one, right? O doesn't move, and so basically VAO is VA, right? So that's the additional information that we're going to get from doing this. I realize I'm going a bit slow, so I'm going to speed up a bit. Actually, before we move on, do we have any questions? Okay. Okay, so next, moving on to general plane motion. So basically in this particular question, we have two sliders. And they're going to move like this kind of, so this one will move from here over to maybe here. This one will move from here to down here, right? So neither of these sliders are fixed in place, right? So yeah, like we can't really do this situation. Usually in these questions, these distances are given, right? So these are known. And therefore, these angles here will be known as well. This is here in particular, we have a right angle. You can just use your sine and cosine geometry. And then, yeah. Okay, so think of it like this, right? This is a bit of an abstract explanation, but this topic is like, yeah, I'm just trying to get everyone to be able to wrap their head around this, because I don't know, it's kind of, it was difficult for me to learn, I guess, the first time as well. You can think of general plane motion as the combination of translation and rotation, right? So pretty much in our setup, this is what's happening, right? We have our member AB, and at node A, it's sliding down. At node B, it's going to the right. But you can think of it like this, right? if we have the velocity of b, except it's being applied to the entire body, right? The entire rigid body, such that this portion is just the translation part, and then the next part represents our rotation. Yeah. Okay. Kind of looks like this, right? So we're going from B to A, right? So I'm calling that omega BA. But this one I'm calling the velocity of A relative to B. So that's reflected in our equation here, right? Okay. Usually you don't have to do this as a step. I'm just trying to fully draw out what you should be, I guess, like thinking of, right? Usually, yeah, anyway, sorry, this is kind of hard for me to explain as well. So yeah, usually this will be a step though. So velocity triangles, it's where you draw out the relative triangle, it's where you draw out the relative velocity equation, but in the form of a triangle, pretty much, right? So that's this, you know. Remember that's the left-hand side starts and ends at that point. The right-hand side starts and ends at that point, right? So everything works out like that. Basically, this angle here, alpha, here's how we would find it. So normally it would be from the relative velocity portion, which you can draw out like a little member, right? And then let's see this compared to the original diagram, right? So there was what we called theta, and there was what we called alpha. And you can see, because of similar angles, that's where alpha and theta sit, right? And that's the arrow that we're drawing here. And so therefore that angle there is alpha. Go away. Okay. Yeah. Okay. So in the case of a right angled triangle, once you get to the step, it's not too bad because you can simply just do this. Right? Basically, in terms of what's known, at this point VB would be known because I was given in the question, and this would be known from what I said earlier, so geometry pretty much. And so all we're really doing is we're solving for VA and VAB, right? In terms of, actually, kind of jumped ahead. One way you can think of it is like, okay, say I want VAB, and we've got VB, so that would be the, this is the hypotenuse side, right? That's the adjacent side. So you go like, because this is adjacent over hypotenuse, right? And we're solving for this, so you go like this. That's kind of thought process, right? And basically in the question, they wanted us to get VA and omega AB, right? So VA was that one, pretty much. And in order to get omega, go like this. Yeah. However, if you aren't given a nice triangle like this, right? So this one's a nice right angle triangle based on this geometry, which was at a right angle here. You're gonna have to use sine and cosine laws. So I have more details on these back from workshop 2, but I've just quickly put it down here. To quickly recap, sine law is useful when you have, two, okay, say you know A and alpha, and you know beta, right? Then you can work out B, right? And B would be one of these, pretty much, for a non-right angle triangle. So sine law, you'll see it used in pretty much most of the worked examples, I think, that I have here. So you'll see that one used. Yeah. Cosine, it's more rare that you use it, but you'll see an example of it used in one of the questions as well. I'll talk about instantaneous center after I finish question 1. So I'll just go to question 1 now. So here's a question. So for this instant represented, so the good news about this particular topic is it's already pretty hard, so they don't introduce time effects. They don't go like at t equals 4 or whatever. It's always going to be a snapshot in time, right? So always going to be looking at something like this. It wants you to determine the angular velocity of link AO, right? Okay, but before we even do the question, we have to think about how the system is moving, right? In order to get the direction for omega OA, right? So is it going to be going that way, or is it going to be going that way, right? So basically, I'm not sure what this machine is called, but it will extend this downwards, right? And that's the direction of V. So that wants to extend. This stays as 90, this rod, right? So it goes like that or something. Maybe like that. And so the machine wants to go this way pretty much, right? So omega OA is going to want to go clockwise, right? It's from observing the system. Okay. Oh yeah, and that stays as 130. So these distances don't change, right? Actually, I'm going to quickly check for questions online. Have any? Doing all right. Do you have questions in person as well? Okay. So here I've just redrawn this on the left. And okay, so what's our first step? Our first step, most of the time, is to find the relevant angles in the triangle, because as you can see, this is not a nice right angle. So this is that's not a right angle, right? Pretty much. Oops. So we're just going to call these angles various things. Call this one theta, that one alpha, gamma, right? Just a quick recap of our cosine, sine laws. Yep, so I've just written them out pretty much. So the big letters stand for angles, and the small letters stand for the side opposite to it, right? So the side opposite to theta would be 0.09, for example. Yeah, so I'm just going to redraw. Just going to draw it out like this. Actually, no, I need. Yeah. So basically, we want to find these angles, right? And we know every side length, right? We can actually choose to use sine law or cosine law because we actually have like enough information for both. Wait, do we? Jokes. I think we have to use cosine law first because we don't know any of the angles, right? Yeah, sorry, my bad. So we use cosine law first. I'm doing it in terms of millimeters, just because that's what I've written down. And we're solving for this angle theta, which is this one here. Next, we're going to use sine law. Right? We're going to solve for gamma. That's gamma. Okay, and then last, I'm going to work out alpha, and that one, we just use the triangle. The fact that all the angles in a triangle add up to 180. Right? So now we have all these angles. That's all good. Okay. So next, I like to think about the velocity vectors. And I like to draw them as well. So link AO I might call that link OA actually. So that's going from O to A, right? Let's draw it out. And so here we have a fixed end, right, at O. So we know that the velocity of O is 0 meters per second, right? It's fixed. And we can write out our relative velocity. Right? So yeah. Anyway. All right. So if we're thinking about what we drew here earlier, we know that omega has to go clockwise, right? So in terms of us drawing out this member, velocity is going to be perpendicular going down and right, because again, we know that this is clockwise, right? And the other thing we know is this angle is theta because of how our similar angles work, right? That's going to be important later for when we draw the velocity triangle. Next, I'm going to draw out link AB. So let's go back up to it. Link AB. I should really call it BA. Not bad. So we're going from B to A, right? So it looks like this. We calculated earlier that this angle was gamma, right? And let's look at our diagram again. So, let's look here. So because this is going down, right? And we can see in our drawing from that state, which drawing was given to us, to what I've drawn over it, that W wants to go that way, right? Angular velocity wants to turn that way, right? So it wants to turn counterclockwise. And that's, maybe we'll draw it more extreme. Might be like that, right? So it goes from that to like that, right? So that would be going counterclockwise, right? I'm not getting like the most positive response in the audience in terms of looks, but yeah, okay, hopefully it will make sense. So basically, that's how we know that W will be going that way, right? And because W is going that way, our velocity will be going that way too. And gamma will be here, right? So yeah, so keep in mind another thing. Basically, do you remember our like butterfly angles that we're talking about way back on the unit circle, whatever? If that's like theta, this here would be 90 minus theta, right? And that's the way you want to be thinking of the velocity vector relative to our lever arm, right? Because yeah, basically, how am I saying that? This angle here is going to be 90 minus gamma, right? And so how I've decided to just draw it in this case is it's changed from the butterfly angle to the other one. Wait. Okay, that was a bad explanation. Okay, you'll see where this goes, right? We knew this from the question, right? And so we don't know what this is. Let's draw out our velocity triangle. Remember, our velocities look like this. And I like to do these little quick doodles of the arrows underneath my equation here, because we're going to have to think about how we're going to actually draw out this velocity triangle, because we're going to have to make all these shapes line up as well as these angles here. Right, so those were from earlier. That's just that angle that I drew there. That's that angle there, right? And that was given in the question. And so when we draw out a triangle, it'll look like this. Right, so left-hand side is like that. So that's VAO. Right-hand side has to start and end at the same point. So this will be VB, this will be AB, right? And this here is gamma, this here is theta, and the other angle for our triangle is alpha, right? So in terms of the question, oops, did I do something wrong? I think I labeled it wrong. Sorry. Oh, no, that's fine. Oh, no, that's fine. Okay. This one is the one which is unknown, but we don't care. This one is unknown, but we have to solve for it, right? And the reason for that is the question's asking for the angular velocity of link AO. So that's that one, right? So we care about this one. Because we're going to need it for our equation with angular velocity, right? So we're going to use the sine rule here to get the magnitudes of these sides. And this is really useful because the other option is to use unit vectors, right? Which we prefer not to do because, I don't know, it turns out to be harder usually, I feel. So sine rule, it's a side that. So that's that side with this angle, and we care about this side. We know this side, and we know that angle, right? So we just replace that. So that's 0.6. Alpha is 108. This is what we calculated in the very first step with the geometry, right? So VAO, when we solve for it, so we move that onto the other side, it's 0.4333 meters per second, right? One more step is apply this formula, right? Because we're solving for omega OA, right? So we just plug in our numbers. That was 13, that was 0.13 meters. In terms of how it looks like this, right? That's that. And we were going clockwise, right? That's clockwise. Okay. Do we have questions? How did the formula for relative velocity change? So I always do it the same way. I'll show you how to. So if it's like VA and VB, you write the one on the left slash the one on the right, pretty much, right? How the arrows work out is pretend VA looks like that. Basically, the left-hand side here has to equal the right-hand side. So if that's VB, for example, then the arrows have to go tip to tail and match at that point, right? That's the way that I always draw it so I don't confuse myself, and then I rearrange it from there, right? Is anyone copying that down? Yeah, sorry. I probably should have started with that. I mentioned it earlier in the relative velocity for particles workshop, but we're going to be using that a lot here, so just, yeah. Yeah. So I have another example, but here's a kicker. It's going to take longer. So I'm just thinking about the break. I might just try to rush through this because we've got a lot to get through, and then I'll give the break after. So yeah, before we look at the question, okay. In instantaneous center, right? Here's how you find it. Firstly, I'll show you how to find it, and I'll tell you what it is. So how you find it is you draw perpendicular lines from the velocity vectors, right? And where they intersect here, that's the instantaneous velocity point, right? So sometimes it's called I, sometimes it's called C. It's basically called I when you have more than 2 points, because usually those points are called A and B, or sometimes OAB, but they're labeled up to C usually, so it's sometimes called I because of that. Yeah, and then the point, yeah, sorry, I already talked about that. So basically the next step is you want to find the radiuses between point A and I, and point B and I, right? Pretend they're lever arm or distance vectors going that way, right? Because pretty much the good thing about the instantaneous center is that it acts like a fixed point which rotation occurs. So pretty much the velocity at I is going to be 0 meters per second, right? And you can treat it like another point. And it's useful because omega I, right? Omega I is going to be the same for between IA and IB, right? So that and that have the same angular velocity, right? And so their velocities are just going to be proportional to this radius, essentially, right? So you can see why this simplifies things considerably, and it's like a nice technique that we can use. So for question 2, okay, we have a rolling disk, which you might have heard of in the lectures, and basically the trick of rolling disks is that here, right, the ground is pretty much where the instant center is. So the entire thing is going to be rotating from there, right? And you might think that it might that it's in the middle, but it's only in the middle for, let's give an example, like a washing machine drum, right? Or something that's spinning about the middle, like that, but isn't moving, right? So because of the translation as well, this this disk is actually in general plane motion. So it's got the translational part and the rotational part, right? So yeah, anyway, that was just a long way of saying that you can use this for your calculations, right? And so basically the question will say that the velocity of the slider is moving to the left 0.25 meters per second. So in terms of how that's making this disk spin, right? So yeah, this will become here. This will go like, it's going to want to go up like to here, right? That whole thing's going to go like there. And it's basically going to want to spin that way, right? That's what I'm trying to say. Oh, sorry. It's about point C. Yes. Yes. Anyway. But this question is particularly hard. I'm not going to lie. It took me ages to figure this out because the question's worded like this. So when the angle is 0, right? So it looks like this. So this this angle is 0 here. Determine the velocity of the center and the angular velocity AB, right? And what you have to realize in terms of, I guess, like, if you want to think about time effects, is that this actually happened before what was presented in the picture, okay? And so yeah, so when I was trying to calculate it, I kept thinking that it span this way, but yeah, it's the other way, right? It's doing this direction the whole time, but the diagram was just a bit misleading as well, pretty much. So I just redrew it with theta is equal to 0, and yeah, so that's your IC there. I'm gonna check online for questions. Okay. Do we have questions as well in person? Or not? Okay. So here I've redrawn everything in terms of just geometry of the distances between points that we know, right? So AC between here and here is just Pythagoras. Right? Let's call this angle alpha, yeah? So you'd find it. Let's call this angle beta. So that's from the rise over run here, rise over run. Okay. Now I want to draw out the velocity vectors. And we'll draw it for link AB. as well as AC. So in other words, I'm going to be drawing it for this one. Right. What I'm going to do actually is call this RBA. That was alpha. Right. And this one was beta. Yeah. Yep. Okay. RCA. Yep. All right. So let's have a think about W, right? I mean omega. Yeah. So essentially, I'll draw it up here. This is AC, right? And this slider is going to be moving left, right? And this is going to want to go like that, right? So, sorry, this is cleanest drawing. Basically, omega CA is going to want to go counterclockwise, right? And BA, right, is this one. So, this wants to go clockwise because the orange line here that I've drawn represents the original state, and then the one that I've drawn in purple is it wanting to rotate clockwise, right? Therefore, just draw it up here. Now we know the directions of velocity. Right? I'll leave it at that for now, and I'll move on to the next step. So yeah, the most important thing was that I found these directions, right? Because it will be useful for our next step when we're drawing the velocity triangle. So we're just going to be focusing on link AB for now. Okay. Let's draw this velocity triangle, right? So VA is equal to VB plus VA relative to B, right? And roughly the directions went like this. Okay. And let's think about these angles, right? Because these angles are going to be a bit misleading. So that angle here, right? This is alpha, correct? But this is 90 minus alpha, okay? Right? And that's what I'm trying to represent here. So remember, the velocity vector isn't the lever arm. I don't really know what to call it. Yeah, it's not the r vector, right? It's perpendicular to it, and so you can't make that mistake. So yeah, so this is 90 minus alpha pretty much. Let's do it over here. So that's actually 67.98 degrees, right? And similarly for VA, okay. Let's say. Yeah. So A, right? So C doesn't move, right? So VA is just going to be this, because VAC is the same as VA, right? So VA is going to be in that direction. And basically, this angle here is going to be 90 minus beta, right? Is that right? Yeah. Do it over there. So it's 33.69 degrees. And then, okay, we'll draw out triangle. So we'll draw from here. VA goes up like that. VB goes to the side like that, right? VAB goes like that, right? As per our arrows that we were drawing. And these are the angles here. So that's 33.69, right? That one is 67.98, right? And this last one is going to be a new angle, which I haven't calculated yet. It's going to be 180 minus these other ones, which is 78.33, right? So 78.33, okay? And so if we apply our sine rule, because we know all these angles now, right? And we know we were given B, right? So we know that one. So we can use our sine rule to get both VA and VA relative to B. So VB was 0.25, right? So when we rearrange for VA, that gives us this, right? Similarly, if we do it for VA relative to B, all I'm doing is I'm changing this to the new angle, which is 33.69, right? I rearrange. I get this, right? Okay. Yeah. So basically, we want to find omega CA, right? In terms of where that is, that's this one, right? And sorry, it's this one, right? So I might copy that actually. So since C is fixed, right? This is what I was talking about a second ago. VA is VAC. So RCA, we can find from Pythagoras. Oh, actually, sorry, I've already done that earlier. So basically, that was the step back here. This one. So it's 0.18, right? So if we look at the relative velocity, plug in that formula, it's this one. VAC that this one doesn't move. And we found VA from the step, right? VAC is just 0.2367 meters per second. And then we know from angular velocity that omega CA is VAC. We've got RCA. VAC was what we just calculated. RCA was 0.18. So that gives us this. Again, counterclockwise because looking at our diagram, right? And yeah, so basically, let's go back to the question. It wants us to find the angular velocity of AB, right? So that's this one. Sorry. It's that one. I'll copy that. So that's going to be our next step. Right? So what I've done is I've just pasted together a bunch of values which we calculated earlier. This is our relative velocity diagram, and that's what our member looked like, right, between B to A. Okay. And so the angular velocity, so this formula, this distance is 0.4, that was given, question. This was what we calculated. That was the step, right? We use the sine rule. Sorry, I'm going a lot faster than usual. Just got a few things to talk about as well. So let's clockwise that one. Right? Okay. Do you have questions? So that was us trying to find the angular velocity. Oh, sorry, I accidentally included a slash there. Of BA, right? Lastly, the question wanted us to find the velocity of the center of the circle, right? So how fast is it going to the left, pretty much, right? And for that, we can just draw this out. So I'm just drawing the geometry again. And luckily, this step isn't that bad because we're purely just using our understanding of instant centers, right? So unlike the relative velocity analysis, this one is quite chill. So as VO, we knew, like, VOC looked like that, right? It's point O, it's point A, radius, whatever. So that. And RCA is that, right? And yeah, the good thing about our instant center is that omega C is omega CA, and it's also omega, I've said CA twice, yeah, OA. It's also omega OA, right? A. CO. Sorry. CO, it's CA, right? Yeah. And so that was equal to that. That was counterclockwise, right? And so simply our velocity of O is going to be our angular velocity multiplied by that lever arm, right? So just plug that in, and relative to a lever arm, right? That gives us the velocity of O. Okay. Do we have questions in person? I can use the sign for velocities. Isn't it used for lengths? I don't know. I don't make the rules. This is how it works. Yeah, it finds the magnitudes, right? That's the important thing. It finds the magnitudes of the velocity triangle. So that's what we use the sign rule for. So what I'll do is I'll give you a break first, and then I'll do quizzes because I feel like we've been sitting here for a while. So yeah, in terms of that, is the tenets. Chill out for a while. Get back, maybe at like 7:20. Oh, okay, time's up. All right, so yeah, just to give a bit more justice to that question, actually, because I don't think I gave a very good response, to be honest. Basically, right, if you think about, okay, VA is VB plus VAB, for example, right? Let's say it goes like this: VA, VB. This would be VAB, right? Yep. Again, this is equal to that, right? So yes, these are vectors which have um, a magnitude and a direction. And if you recall the first workshop that we talked about forces, right, which was just a type of vector. Yeah, you know that like there's kind of two ways to find magnitude, right? First way, well, we really only talked about it in terms of right angle triangles. Yeah, okay, so say, actually, better yet. Let's do it in terms of right angle triangle, right? So that's the same thing. We basically can use Pythagoras, right? For that side to get the magnitude of that. And we're doing a very similar thing with the sine rule or the cosine rule to find the magnitudes of these arrows because, you know, pretend you did it like this, right? Pretend we knew the magnitude was like 6 and this one was like 4, right? Yeah, I didn't pick the most exaggerated numbers, but you can tell that is not equal to 2, right? You can't subtract it if they're like facing in different directions and stuff. So like I guess one way to do it is draw it out and find the magnitudes based on geometry. The other way to do it is you can do it in terms of unit vectors, right? So that's like negative I something. It's like J or whatever. Yeah, then you can do a calculus in terms of unit vectors, and then you can use Pythagoras on those unit vectors to find the magnitude. Yeah, basically we just want the magnitudes of these arrows, right? One way or another. And I think the easier way of doing it is using geometry. Yeah, including using the sine law, right? Yeah. If that makes more sense. What I'll do. Let's paste it in. Okay, so we're gonna move on to quizzes. We have time for anything. Yeah, sorry. So I made this one less hard than last workshops, but still like the concepts I guess is still a bit hard. So if you could just scan this, please. Um, yeah, the concepts themselves are harder, but I made the questions easier. But hopefully, if you do this, it'll give you a better understanding of what you should be thinking about step by step. I'll just give like a few more seconds for more people to join. Okay. Yep. This course is hard. I do want to say though, question 2, the one that I just did, that's exceptionally hard for a question. So if you're looking at that and being like, oh man, I'm gonna drop a course, yeah, it's fine. That was an exceptionally hard question. Out of the extra practice that I've given, you'll find those ones are a lot easier than that question. I think most people are done, so I'll give like a few more seconds for people to finish up. Sorry, yeah, I'm gonna have to finish up. Just conscious of the time. Okay, congratulations to these people. Very well done. Okay. Let's look at the questions. Oh man, yeah, it's getting up there. Bit right skewed, what it was called. Okay, yeah. So for the instance center, it's basically not parallel to the velocity vectors like in situation on the left. It's perpendicular to them, right? And so our velocity b goes down the incline. Our velocity a will follow the wall, right? And so perpendicular to that will be that point there. Zoom in. So yeah, the angular velocity of BC, so that's from B to C, right? And that's clockwise. Yeah, because that slider will want to move to the left. And yeah, it's just gonna turn clockwise. Which members are undergoing general plane motion? So that's simply only AB. So BC, sorry, I should call it CB and OA are rotating about a fixed axis, right? And those are the pinned supports there. So those ones are not general plane motion. In terms of some quantity of unit vectors, angular velocity, yeah, so this is kind of like a segue one because I'm going to talk about this more after this quizzes, right? But essentially it's in the positive direction. So let's look at WO, right? So if you do the right hand rule and you match your fingers up with the direction of where the arrow is going for for omega O, you'll see that's pointing towards you, and that's the positive k direction, right? So the vector's pointing at the viewer. Okay, cool. Let's get back to Discord. Let's look at this question, right? Here, yeah, basically it looks kind of scary, but it's not too bad. The idea is that we have this 2D rigid body, which is triangle, but we can effectively just treat it like a 1D rigid body. And the reason for that is because only really this link here matters, right? Between A and B, right? The rest is just fluff, pretty much. Yeah. But another important thing is we're gonna have to find the velocity and acceleration of the center of roller B, right? So that's those two. And we're gonna have to calculate the angular velocity and angular acceleration of the plate, right? So that's that. In terms of information that we're given, theta is 30, right? So that's a snapshot in time that I was talking about. And the cylinder is going to be moving at a constant rate of 0.3 meters per second. So that's going to affect A, right? So actually that number there, AD, is undergoing just translational motion pretty much, right? In terms of formulas, because you haven't seen them before, I'll just write it out here. But they're included after this question as well, in a more like succinct way, I guess. So the first one is that you can look at acceleration vectors, relative vectors, in the same way that you can for velocity vectors, right? So the acceleration of A is equal to acceleration of B plus A relative to B. The next thing you can do, let's do this first. Yeah, sure. Is you can do, you can split up your acceleration, your linear acceleration, in terms of its normal and tangential components, just like with particles, right? Except in this context, we're going to be doing something more like this, which is, looks a bit scary, but it's not too bad. Basically, we're going to be splitting up the acceleration of A relative to B into its normal and tangential components, right? Which would look something like this. And so this is the normal component, and this is what the tangential component is equal to in terms of formulas. I don't know if we've seen these before in lectures, but here they are now. But yeah, I'll leave that up there. Okay, so what I've done is, to save time, I've done the velocity part already. So the first step to solving any question which involves acceleration is to solve for velocity and angular velocity first, right? Like components which are relevant to the acceleration part. That's always the first step, right? Unless you're given it, in which case you don't need to solve for it. But yeah. In terms of, so for people copying this down, yeah, sorry, it's, I'm gonna not really have time to really like let this, actually I'll go through it briefly. So yeah, we know that the angle is 30 degrees, right? We're given that in the question. So at that snapshot in time, VA is 0.3, and we were given that because of what we know about how the cylinder is constantly going up at 0.3, and yeah, because that's going up, this is going to want to spin counterclockwise, right? Leading to omega BA, being counterclockwise, and therefore the relative velocity of A to B going in that direction. Now I've drawn the velocity triangle where we know A, right? We know A, and so we can solve for B using, since this is a right angle triangle, right? Because this one's only going to the right, this one's only going up, so it will result in a right angle velocity triangle, right? Then we can find VB and V of A relative to B based on what we know about sine and cosine and like right angle triangles, right? Okay. So next, angular velocity. Omega of the plate, right? So the question wanted to find the angular velocity of the plate, and the angular velocity of the plate is just going to be the angular velocity of BA. So do you remember how I said earlier that triangle is basically just fluff? Well, it's because we're just focusing on that link there, which is between B and A. Put in our formula. So we know that from here, right? We know that the triangle sides are 0.2 meters. That's 1.732 radians per second counterclockwise, right? Counterclockwise because, you know, that's going up. It's going up. The triangles want to go like that, which is counterclockwise, right? Like the triangle wants to spin counterclockwise, right? Next is angular acceleration. Very similarly, angular acceleration of the plate is equal to the angular acceleration of BA, which is so do you remember that formula I wrote earlier? From here, wrong one. Did I write the wrong one? I think I wrote T by accident, but I meant N. Sorry, that's an N. Right? So we want to find this pretty much. We're going to store this equation under 1 for now because we're just going to find the normal component of acceleration A relative to B. Okay, so from what we know of relative acceleration, so A was the cylinder, right, which we know is moving at a constant velocity, right? So therefore the acceleration of that is going to be 0, correct? And for B, that can only move to the right due to the constraints of this little slider, right? Therefore, when we rearrange for acceleration of A relative to B, that's going to be equal to negative B, right? let's draw out a triangle, right? And this was point A on our triangle, right? Essentially, it's going to look like this. It's a tangential component. Okay, sorry, my bad. That should be a straight line. Okay, so I've drawn it out, and I'll try to explain it now. Basically, acceleration of B went to the right, right? And so this one has to go to the left. Which is this arrow, right? So it's going to the left. And our components of it look like that, right? These are our formulas, right? Sorry, BA, right? And that just equals 0.6, right? So yeah, that was for A acceleration of A relative to B. But if we want the acceleration of B relative to A and the normal component, right, that's going to be 0.6, but pointing that way, right? So they're just opposites of each other because I've swapped around A and B, right? So I'll just redraw that here. So those components split up and look like this. Right? So we calculated that as 0.6. And in terms of angle, this angle is given us 30 degrees, right? So pretty much ends up looking like this. This one is 30 degrees, this is 60 degrees, 30, 60, right? And so we can solve this using our understanding of right angle triangles. Oops. That's not a good way of doing it. But that was 0.6, right? So that gives us this, right? So that's yeah, that's that component, right? And we can also get the tangential one. Do we need the tangential one? No, we don't. All right. So basically, returning to that equation which I stored earlier, which is what they were asking for, the angular acceleration. Let's plug in this. And in terms of, so before we were talking about this being counterclockwise, right? The angular acceleration like that. Yep, for very similar reasons, talking about the angular velocity, for very similar reasons, the angular acceleration is also counterclockwise. Sorry, I'm rushing through this. Yeah, that was only 3 questions. Oh my goodness. You don't know how much more I have left prepared. Do you have questions first? Sorry. It's a bit of a tough workshop. You do have a question? Oh, sorry, you have to ask. Yeah, I've no idea what to expect in the finals, so I'm just trying to cover all the bases. Right? Okay. So for the next bit, I might just, in the interest of time, I might not do the question, but I'll show you the thought process, right? So pretty much, I don't know, the working for this question, the acceleration part is honestly easier to do using unit vectors, right? So I've done it the non-unit vector way. I've shown you what you can think about it this way, which you can avoid unit vectors entirely, but I think unit vectors is actually more useful for solving the acceleration part of questions, right? So yeah, remembering that there's a third dimension for unit vectors, k, which we haven't really talked about except like briefly. Like I mentioned it in the quizzes pretty much, right? So the k dimension, the positive direction would be pointing towards the viewer, the negative direction would be pointing into the page. So when you cross multiply these unit vectors of these directions, right, you're going to get like either a positive or a negative, right? So that's what I've drawn out here. So on the left is like the positive products, on the right is the negative products, right? So that's just these flipped around, right? And this is going to be important because if we're going to be using unit vectors, we're going to be using cross multiplication. Cross products, right? So here's where the cross product is. So it's only for the tangential component, right? And this is for the case of fixed axis rotation, right? So that's from here to here, right? This one I'll talk about briefly, but there's just an extra component out the front here that you add on. So in the case of this fixed one, if you want more details, please just refer to this YouTube video. I suspected that I wouldn't have time to cover this, so you can look this up. It's called Rigid Bodies Relative Motion Analysis, right? They do it the unit vector way, pretty much. Okay, here's the deal. So because this is counterclockwise, right? This is going to be a positive k, right? And then when you cross multiply positive k by positive I, let's go up to our table. That's this one. You get positive j, right? And so that's what I've labeled here. But when you multiply k by j, right? K by j, you get negative I, right? And so that results in the negative here, right? But yeah, it's really just about plugging in the formula and doing a bunch of grouping together I and j components. And then you end up with this, right? That's for the first part. But for general plane motion, so that's for rod BC, that's this one here. So that's not fixed, right? And so you have to add on this extra component. And then you're going to split the relative motion portion into its tangential and normal components. All right, here's where it gets a bit funky, right? So since AC is purely going to the left in the I direction, we've made that negative I, so that when we solve for it, that's just going to be the magnitude. K, okay, let's not look at any of these out the front here first. So K multiplied by I, right, go to our table. K and I gives positive J, right? Now we have to account for the negative here, and that gives us a negative in our product, right? Similarly, K and J gives us a negative, right, when we look at the table, right? However, there's a negative here, and there's a negative here, which cancels out. So we're just left with the negative, right? Yeah, and then once you've grouped them to the best of your ability, you'll notice that there's two unknowns. There's AC and there's alpha BC, right? And so we have to compare the I directions and the J directions. And the one we do first is J, right? To do that, we take all the J components on the left, which is nothing, so that's 0. And then we take all the J components on the right, so that's 3 point whatever. And this one, right? And then we can solve for alpha. So once we have alpha, we can do the same thing for the I components, sub in the alpha that we just worked out. So I think this is a better way. Like in my solutions, I did it this way compared to the way that I outlined in question 3 just now. I think this way makes more sense, to be honest. It's a bit tedious because you're gonna have to do a lot of cross multiplication, but you'll find that it's like, I find like you get the answers more consistently, right? Yeah, does anyone have questions about that? No. But you can still do the velocity part without involving unit vectors. I think that's easier without unit vectors. Yeah. All right, just gonna choose to ignore what I read. Okay. Okay. Some more to talk about. I'm gonna go back to my other slide. Yeah, you'll have to excuse me for the people in person here. I might go a little bit over time, but I'll try to keep it under 5 minutes of time. So, because this is important, right? This is important because it's gonna lead on to our next topic. The mass moment of inertia, right? Technically, this is a part of kinetics, but kinetics, we're gonna have a lot to talk about as well. So I wanted to split it up, and if you want to have like a little bit of a head start with the homework, then in the extra questions, there's a portion just for mass moment of inertia. I think just like 2 questions or something. So the idea is a mass moment of inertia. The equation looks like this. Yeah, it's about a point, right? And this is the center of gravity of an object. So I'll show you what I mean, right? You see in the next question, question 5, which I'm going to do. Say there's like a pendulum, and it spins about this point O, right? And the center of gravity, there's 2 objects, right? There's this rod, and there's this disc, right? Center of gravity is going to be different for both of these objects, right? Actually, I'm not going to overcomplicate it. Let's just do for that rod, right? Basically, that D is going to be the distance between your point of rotation and the center of gravity. But to get it for the entire composite object, so before we're talking about a disc on the end of a rod, you'll see how that works, but you're going to have to kind of add up the IOs, right, of all the objects. So this is the shift distance. That was the mass. So here's the thing. IG, or sometimes the formula is given an IO, it will vary per shape. They've done like calculations, derivations or whatever of how they get all these shapes, but I've included the common ones here. Specifically, I highlighted them in blue, underlined them in blue. So this is your axis, right? And for a disk, you're talking about R pretty much, right? That's the radius. And you're usually given the mass of the object as well. So that's what you slot in for M. The rod about its center, for example, would be like that. That's a rod about its center, right? We're talking about the center of gravity there. But if we wanted to do it rod about the end, what was the formula? Yeah, you could do like this instead. You can pretend G's there and then just plug in the rod about its end formula instead. Right? Yeah. Because it just cancels out the shift distance pretty much, right? Okay. So I've talked about how you get it, how you like calculate or whatever. I'm going to talk about what it is, right? Because, I don't know, conceptually, firstly, I like to talk very like conceptually, but it helps me to understand what it is with this definition. So it's essentially a measure of an object's resistance to rotation, okay? And it's equivalent to mass in Newton's second law, but for moments, okay? So I'll draw what I mean. So that's important because it's to do with Newton's second law. That's where we're going with this. That's the first part we're going to be talking about in kinetics on Friday, right? Okay, so like we said, for rigid bodies, they still have translation, right? They still have these Newtonian forces which you calculate, right? But they also have rotation, right? And that's where IO slots in. So it's equivalent to mass, but for rotation. But to even get that number, it's kind of hard. You have to jump through quite a few hurdles because it's very shape dependent, right? How an object rotates is very shape dependent, and it's going to determine how much resistance it's going to have to rotation, right? And about which point you rotate it. So that's what I is. Think about it like this as well. Mass. Okay, so you have a box. So you have a box and you're pulling it with a constant force F, right? If I increase that mass, it's going to accelerate less, right? If I decrease that mass, it's going to accelerate more, assuming our force is constant. So you can think of mass like a resistance to being, to forces, right? Like things moving it around. So similarly, you can think of moment of inertia, mass moment of inertia. That's moment. That's big M's for moment. Think of a box being rotated, and there's like an external moment that's being applied to it. It's how much angular acceleration there will be. If I increase the resistance to rotation, I, we're gonna have less angular acceleration, right? And if I decrease it, we're gonna have more angular acceleration, right? That's kind of how it works. And yeah, just conscious of time, I'm going to rush through this question again. So here's that pendulum I was talking about. We're given the masses of both the objects. So there's a composite object, right? So I of the rod is going to be IG of the rod plus the shift distance, right? Let's draw that out. So it's rotating about O. It's G. That distance there is going to be 1, right? Correct? Oh, I'll do it again. So basically this formula we get from that diagram I showed. We plug in our mass, which was 2. We plug in our length, which was 2 meters. Our distance was d, which I drew over here. And we get that I of the rod is this. Right? And of the plate, which is our disk, right? Let's draw it out. O was over here. Then there's a bunch of space separating it. And its center of gravity is here, right? In terms of distances, right, this was 2 meters and this was 0.5 meters. So it's 0.5 meters because it only goes halfway, right? So D is 2.5, right? We look at that table and we get the IG for a disk cylinder. Right? That was 4 kilos. The radius, right? 0.5. D was what I calculated for, right? That gives us 25.5. Yep. All good so far. So IO of this composite object, right? All you do is you simply add up all of your individual shapes. So each of the shapes is going to, like, having added on the shapes is going to increase its resistance to rotation, right? To some degree. Right? So all I've done is just added up that and that. That gives us that. Lastly, radius of gyration, denoted by K. This is what the question asks for. I'll explain that in a second. Here's a formula for it. So we rearrange. Where M is the mass of our composite object, which is 4 kilograms plus 2 kilograms, right? So that's the mass added up for the total composite object. Okay, so radius of gyration. This is also kind of a difficult concept to understand, similarly to IO. Here's how I like to think of it. So it's a measure of the spread of the mass relative to our point of rotation. Okay, so given the name, you can think of it like a radius. So our number that we got was 2.167. So if I overlay it, it's up there. Right. Give it kind of like that. It's not very circular. I don't know. This kind of helps. It's just a measure of how far away the rotational resistance is from this where it's rotating, pretty much, right? Yeah. That's pretty much all you need to know about it. Just the formula. Yeah, in order to do the questions. But yeah, if that makes sense. Okay. Yeah, for people in person, unless you got questions, you can go. Thank you for your time. I know I went a bit over time today. I know I did the questions quite quickly as well, but those those rigid body kinematic questions are quite hard, I reckon. I provided some extra questions, extra practice as usual. Those ones are generally a bit easier, but there's also some hard ones, including ones for acceleration. Yeah, I'd recommend you practice those before your finals. Yeah, it's definitely by far the hardest topic. As you can see from even just this bit at the end here, next lesson won't even be this hard, right? Just today's lesson was particularly hard. So congrats, you made it through. Same thing with people online. Unless you got questions, you're free to go as well. Yep. Yep. But yeah. Otherwise, thank you.